So far, we've looked at the Fourier series of functions with a period of 2 pi. In this lecture, we're going to extend those ideas to functions of arbitrary period, as we're going to see the formulae for functions of arbitrary period are going to be very similar to the formulae for functions of a period of 2 pi. So by the end of this lecture, you'll be able to calculate the Fourier series for a wider array of different types of periodic function. And then we're going to apply those ideas to calculate some interesting series for some transcendental numbers like pi and pi squared. So let's take a look at the Fourier series for a periodic function with an arbitrary period. Now we're going to express the period as 2 times L. So if we can identify the period of the function, we're going to express it as 2 times some value L, and we're going to call L the half period. All of these expressions here have a much neater form when I use the half period rather than the period. So you can see that the form is very similar to what we've seen before. Again, just we've inserted this factor of L over pi, or pi over L, in these formulae. Notice also that the integrals for a0, an, and bn are now going from minus L to L. So remember that the period is 2 times L, so my integrals are from minus L to L. It's worthwhile pointing out here that I could always set L equals to pi to get back the formula for a period 2 pi function. Remember, if L is equal to pi, then the period is 2 pi, and I actually get back exactly the same formula as the ones that we've been dealing with before. Now these are actually the formula that will be provided to you in your exam papers. So as long as you can use these formula, you won't have to remember much else. So let's try and apply these now to some periodic functions with arbitrary periods. Taking a look at example 1, we have a function f of x is equal to the absolute value of x between minus 3 and 3, and it's got a period of 6. Again, we're reading that off from this expression here, which tells me that every time I move over by 6 units, I get the same function again. So I can immediately read off from this what the period of the function is. So t is equal to 2 times L, which is equal to 6, which means that the half period L is equal to 3. So that's the value of L that we're going to use in those integral formulae. So we're going to sketch this function and find its Fourier series, and hopefully take advantage of symmetry in the function if we can. So let's take a look at what the sketch of this would look like. So we're going to sketch it between minus 9 and 9. The function is defined between minus 3 and 3 as the absolute value of x. So for positive values of x, that's not going to do anything. And for negative values of f, it's going to change the sign so that I get a positive number. So that's the absolute value of x between minus 3 and 3. And now we're going to pick up that and we're going to copy and paste it to create a periodic function. All right, so our function is just going to repeat itself. It's a little zigzag. You can see that there's no discontinuity, so I don't have to worry about open circles and closed circles. The whole function connects up with itself. Although it is changing discontinuously at the edges, as you can see, at these little corners. It's changing its slope discontinuously. So here's my function, f of x. And we can see that this function is going to be periodic. If I swap it left-right, I end up with the same function. So f of x is an even periodic function. And we saw in the last lecture that that means that a number of the coefficients are going to go away. So specifically, because f is an even function, That implies that all of the bn's, which are the coefficients for the sine of n pi x over L, those are going to be equals to 0. Sine is an odd function, so f of x can only be made up of even functions. So that leaves us with a0 and b0 and an. So let's take a look at the a0 for this period 6 function. So the period is 6, so the half period L is going to be 3. So 2 times 3 is 6. Integral from minus 3 to 3 of f of x dx. Now remember, of course, that f of x is an even function, so I can replace that integral from minus 3 to 3 with an integral from 0 to 3 and then multiply the answer by 2. And the advantage of writing it like that is that the absolute value of x, when x is between 0 and 3, it doesn't do anything. It doesn't change the value because x is positive between 0 and 3. So I can write down a single explicit formula for f of x equals to the absolute value of x between 0 and 3. So 2 over 6 is 1 over 3. The integral of x is x squared over 2. Evaluating that between 0 and 3 and sticking in values of x equals to 3 and x is equal to 0, we're going to get 9 divided by 6, which is going to be 3 over 2. So that's a0, and it's going to be the average value of my function. And we can actually see that if I was to sketch a horizontal line here. The average value of my function would be right in the middle. So that's a0. Let's take a look at an. Now the formula for an for a function with a half period of L equals to 3 is going to be 1 over 3 integral from minus 3 to 3 of fx cosine, and we have to put in the correct formula here, so it's going to be n pi x divided by 3 all times dx. Let's take advantage of the symmetry in the problem. F of x is even, cosine is even, so the integrand is even, and I can write this as 2 times the integral from 0 to 3. Again, f of x takes the value x between 0 and 3, because absolute value doesn't do anything, multiplied by cosine n pi x over 3 dx. And this is again a standard integration by parts. So carrying out that integration, we're going to get 2 over 3 times u times v. So we have to be a little bit more careful now because the argument of cosine is a bit more complicated. So it's going to be sine n pi x divided by 3, let's put that in brackets, all divided by the thing multiplying x. So that was n pi divided by 3. And that's going from 0 to 3. So that's uv. Now let's take a look at v du. So I've got the integral from 0 to 3 of v du. So v is sine n pi x divided by 3 all over n pi divided by 3. And that's multiplied by du. Okay, so let's see what we get here. We're going to get, let's take out that n pi over 3. Of course, it's dividing on the bottom, so it comes out and it gets flipped upside down. So I get 2 over 3 times 3 over n pi. Division by a fraction is the same as multiplication by the reciprocal of the fraction, multiplied by x times sine n pi x over 3 from 0 to 3. Minus, again, I can take out that n pi over 3 and turn it into a reciprocal. And I've got the integral of sine n pi x over 3, and that's going to be minus cosine n pi x divided by 3 all over n pi divided by 3 from 0 to 3. So put in the values of x now. We've got 2 over 3 times 3 over n pi, so it's going to be 2 over n pi. I've got 3 sine n pi 3 divided by 3, so that 3 will cancel this 3. Minus, when I stick in x is equal to 0, I'll get 0 here. Let's take out this factor of minus n pi over 3, so that's going to give me plus 2 over n pi, and again that factor of n pi over 3 on the bottom becomes a multiplication by 3 over n pi, times cosine, let's put in x is equal to 3 into this, we're going to get cosine n pi minus cosine of 0. So we know that sine n pi is 0. Cosine n pi is going to be equals to minus 1 to the power of n, and cosine of 0 will be 1. So that's going to give us 6 over n squared pi squared minus 1 to the power of n minus 1. And that's our an. Now, as we've seen in previous examples, when we end up with a situation like this where there are certain values of n where I'm going to get 0 here because there's going to be a cancellation between these two factors. Whenever that occurs, I should really look at separately the case of n equals to odd and n is equal to an even number. So let's take a look at n equals to 2k plus 1 equals to an odd number. So here I'm setting k is equal to 0, 1, 2, 3, and so on. So I can pick up all of the odd numbers. Then the coefficients corresponding to that value of n will be equals to 6 over 2k plus 1 squared, pi squared, times minus 1 to an odd power is minus 1. Minus 1 is going to give me minus 2, so I can write this whole thing as minus 12. Whereas for n is equal to an even number, so n is equal to 2k, so here k is equal to 1, 2, 3, and so on, then a for those values, an for even n, is going to be equals to 6 over 2k squared pi squared times minus 1 to an even number is 1, minus 1 is 0. So this whole thing is equal to 0. So all of these even n-a's, coefficients, those are going to be equals to 0, and I'm only left with the odd ones. So if I write those out explicitly, let's see what I get. So we're going to get f of x is equal to 3 over 2, that was our a0, plus the sum from k equals to 0 to infinity, (6 over 2k plus 1), oh, that's a minus 12, sorry, squared, pi squared, all multiplied by cosine 2k plus 1 pi x over 3. So it's a bit of a complicated looking formula there. But by looking separately at the cases of x odd and x even, we've managed to find the proper expression for the Fourier series of this function. Now, what we're going to do next is we're asked to calculate or to figure out what the value of this function is at x is equal to 0. So first of all, let's take a look at our figure here. At x is equal to 0, you can see there's no discontinuities in this function, so the Fourier series is not going to do anything strange. We've got just the value of the function is equal to 0 at x is equal to 0. So at x is equal to 0, f is equal to 0. But what happens to the Fourier series? So I've got 0 is equal to 3 over 2, and let's now substitute in x is equal to 0 in here. So we're going to get minus 12 over 2k plus 1 squared, pi squared, times cosine of 0. And of course cosine of 0 is 1. So I have an expression here that involves some numbers, it involves pi, it doesn't involve any angles, it doesn't involve x. So let's see if we can write out what that looks like. First couple of terms. So we've got 3 over 2, let's take out that factor of minus 12 over pi squared. Again, cosine of 0 is just 1, so I don't have to worry about that. And let's think about what this factor 1 over 2k plus 1 squared is. Well, remember that we're summing up k is equal to 0, 1, 2, 3, 4, 5. And 2k plus 1 was exactly the expression that we used to come up with the odd numbers. So these expressions here are going to be 1 over 1 squared, 1 over 3 squared, 1 over 5 squared, 1 over 7 squared, and so on. They're going to be the sum of 1 over the odd numbers squared. So I can write that as 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared, and so on. Now all of this is equal to 0. So I can actually rearrange this expression now to actually get a formula for pi squared. Let's multiply, let's bring the 3 over 2 to the left-hand side and multiply everything by pi squared over 12. So I'm going to get pi squared over 12 times 3 over 2 is equal to everything that's left behind. So that was 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared plus and so on. So what does this thing on the left-hand side become? Well, I've got pi squared. The 3 is going to cancel one of the factors of 3 and 12, so that'll give me pi squared over 12. Multiplied by 3 over 2 is pi squared over 8 is equal to 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. And so I've actually started getting a formula here for pi squared over 8. And this is actually kind of amazing because all I did here was I took a whole bunch of just the natural counting numbers. I took all the odd numbers, I squared them, and then I made a series of 1 over each of those squared odd numbers. And I ended up getting a formula here for something that's kind of mysterious, right? It's pi squared. It's a sort of a fundamental number that appears in mathematics. So we were able to derive, using Fourier series, an infinite series expression for pi squared. Let's take a look at example 2 and apply these ideas to another example where we have a function with an arbitrary period. This time between minus 1 and 1. We're going to find the Fourier series of this thing, and we're also going to derive another formula for another kind of mysterious expression here. We've got pi over 4. So our function is just x between minus 1 and 1, so that's going to look as follows. So we're going to sketch this between minus 3 and 3. So between minus 1 and 1, this is just the increasing function with a slope of 1. It's going between 1 and minus 1. And then that thing is just going to repeat itself. Now we have to deal with the discontinuities. In this case, we do have discontinuities. So following the formula that we're given, we're going to include the lower points and exclude the upper points. So let's use our sketch here to identify the period of the function. We can see that the width of my basic tile here is 2. So the half period, which is just half of that, will be 1. And that's the L that's going to appear in our formulae for the coefficients. Let's also think about what the symmetry of this function is. Clearly, f of x here is an odd function, which allows us then to write the Fourier series as a Fourier sine series. That is, because f is an odd function, it means that the a0s and the a_n's will be equals to 0. And my Fourier series is only going to be expressed in terms of the bn's, that is, the coefficients of the sines. So we've got 1 over L, integral from minus L to L, I'm using L is equal to 1 here, of f of x sine n pi x over L. So we can simplify that a little bit. This is going to be the integral from minus 1 to 1 of f of x sine n pi x. In fact, I know what f of x is. It's just x. dx. Let's make use of symmetry. We know that x is an odd function. And I know that sine is an odd function, and an odd function by an odd function is an even function. So the integral of an even function is going to be equals to 2 times the integral from 0 to 1. Hopefully that's going to make our life a little bit easier. Now we can make use of integration by parts. So we're going to set u is equal to x, dv is all the rest. So carrying out that integration by parts, we're going to get 2 times u times v, so that's integral of sine n pi x is minus cosine n pi x divided by n pi. Minus 2 times the integral from 0 to 1 of v du. So that would be minus cosine n pi x over n pi dx. So let's take out that minus 1 over n pi. So I get minus 2 over n pi x cosine n pi x. 0 to 1. Again, let's take out the minus 1 over n pi. Integral of cosine n pi x is going to give me sine n pi x over n pi. 0 to 1. Putting in the values of x, I'm going to get minus 2 over n pi x is equal to 1 times cosine n pi minus x is equal to 0 plus 2 over n squared pi squared sine of n pi minus sine of 0. So those will be equals to 0, leaving me with minus 2 over n pi. Cosine of n pi is minus 1 to the power of n. Or if I write that as 2 over n pi times minus 1, that's minus 2 over n pi, multiplied by minus 1 to the power of n. Then I can write, using the laws of powers there, I can write that as 2 over n pi minus 1 to the power of n plus 1. Okay. So my Fourier series then is going to be f of x is equal to the sum from n equals 1 to infinity 2 over n pi minus 1 to the power of n plus 1 sine n pi x. So there's no cancellation here, so I'm going to have to include all values of n, both odd and even. Now in the next part of this question, we're asked to see what happens to this function at x is equal to 1. So let's take a look. So at x is equal to 1, this is part 3 of the question. We have two options. First of all, we could look at our sketch, or we could look at the Fourier series. If we look at our sketch, however, we know that our function is actually discontinuous at the value x is equal to 1. So I don't actually have, I have a value defined for my function, which is given by this point down here. It's given by minus 1. But what we're looking for is what the value of the Fourier series is at x is equal to 1. So let's see what would happen if I was to put x is equal to 1 into my formula for my Fourier series. So I've got f at x is equal to 1 is equal to the sum from n equals 1 to infinity of 2 over n pi minus 1 to the power of n plus 1 times the sine of n pi. But we know that the sine of n pi is equal to 0 for any integer value of n. So I've got the sum over n equals 1 to infinity of 0. So I've got 0. So my function converges to the value f is equal to 0 for the Fourier series. So this is kind of a contradiction. My function is defined in such a way that the value of the function is minus 1, but the Fourier series takes the value 0. And the reason it does that is because my function was discontinuous, but the Fourier series is built up of things that are continuous. It's built up of sines and cosines. So whenever I have a discontinuous function, I'm always going to end up with a Fourier series that's continuous. In other words, the Fourier series is trying to fill in those discontinuities by jumping back from 1 to minus 1, from 1 to minus 1. So how does it figure out what the value is at x is equal to 1? Well, it just takes the value halfway between. So that's a very useful and important result, that the Fourier series is continuous, which means that the value of the Fourier series at a discontinuity converges to the point halfway between just before the discontinuity, so we write that as 1 minus, and halfway to the point just after, 1 plus. So in this case, the value of the function just before the discontinuity, let's take a look again. The value of the function just before the discontinuity is equal to 1. The value of the function just after the discontinuity is equal to minus 1. So if I stick in those values, I'll get 1 minus 1 over 2. I'll get 0. So that's one of the important properties of Fourier series, is that even if you feed them a discontinuous function, the Fourier series will always have to be continuous. So it'll have this property that the function will converge to a value of the function that's halfway between the values on either side of any discontinuities. Let's try this also for x is equal to a half and see if we can derive an interesting series. So we have at x is equal to 1/2. I can again put in x is equal to a half in here. Now there's no discontinuity at x is equal to a half, so the value of my function at x is equal to a half is just x, it's just a half. So I'm going to get this is equal to 1/2. And this is going to be equals to, from my Fourier series, the sum from n equals 1 to infinity of 2 over n pi minus 1 to the power of n plus 1 times sine n pi x. So this time x is equal to 1/2. Now sine n pi over 2 was one of the series that we looked at in an earlier lecture. It was equal to 0 for n is an even number, and it was equal to minus 1 to the power of k for n odd. That is, n is equal to 2k plus 1. So we can check that. For k is equal to 0, 1, 2, 3, and so on. So we can check that. Let's put in n is equal to 1, so that would correspond to k here equals to 0. Then I'm going to get sine of pi over 2, which is 1. And according to this formula, that would be minus 1 to the power of k. So k is equal to 0. Minus 1 to the 0 is 1. For n is equal to 2, I'd have sine of pi. That's an integer times pi, and so the sine will be equals to 0. For n is equal to 3, that corresponds to k is equal to 1. I have minus 1 to the 1, and I get minus 1. And so on. So I'm actually going to rewrite this whole Fourier series here in terms of k's, because whenever n is an even number, I'm going to get 0, so I can just write this whole thing in terms of n being an odd number. That is, n is equal to 2k plus 1. So let's replace n with, the summation is being replaced with k equals 0 to infinity. The values of n is being replaced with 2k plus 1. Let's take a look at this factor of minus 1 to the power of n plus 1. So n is an odd number. We know that from this expression here. N is an odd number, so n plus 1 is going to be an even number. So minus 1 to an even number is just 1. So that leaves me with sine of n pi over 2 for n equals to 2k plus 1. So we saw that that was equal to minus 1 to the power of k. So let's write out a couple of the terms in this expression. We're going to have factor of 2 over pi out the front. And then we're going to have minus 1 to the power of k divided by 2k plus 1. So for k is equal to 0, that would be 1 over 1. For k is equal to 1, I'd get a minus 1 from this expression, and I'd get 1 over 3. K is equal to 2 would give me minus 1 squared, give me positive 1 over 5. And so you can see I'm getting plus or minus 1 over the odd numbers. Once again, I can rearrange this whole expression here. This thing is equal to a half. So if I multiply both sides by pi over 2, I end up with pi over 4 is equal to 1 minus a third plus a fifth minus a seventh, and so on. So we have an infinite series expression for pi over 4. So we saw in this lecture that you can actually use Fourier series for functions of arbitrary period and then form infinite series for expressions involving pi and pi squared. We also saw that when we're dealing with a discontinuous function and we calculate its Fourier series, we actually end up getting a continuous function. And the reason for that is that the Fourier series is built up of sines and cosines. And those are automatically continuous functions, which means the Fourier series has to be continuous. So the question then is, what happens at discontinuities? Well, in that case, our function is going to converge to a point halfway to halfway between just before the discontinuity and just after the discontinuity. So in this particular example here, our function converged to, at the discontinuity at x is equal to 1, our function converged to 1 minus 1, it converged to 0. So that allows us to deal with the Fourier series of discontinuous functions.